Greetings all. Today we are going to learn about some important terms that is used in coordination compounds. So we are studying about coordination compounds. For example, consider this coordination complex. Cobalt, hexamine, or so there are mainly three terms that are used. One being coordination entity, second the central atom, third the ligand. So we'll see what all these things are. First, coming to the coordination entity. Coordination entity means all the constituents of this double bracket. So in a complex, coordination complex, the metal atom as well as the groups or atoms or molecules that are directly bound to it are collectively called as coordination entity. So in this complex, this part is known as coordination entity. Central metal atom plus ion or molecules that are directly bound to it. For example, COCl3 NH3 three times. So this complex, the coordination complex is a cobalt ion surrounded by 3 ammonia molecules and 3 chloride ions. Here, this coordination entity is a cobalt ion surrounded by 6 ammonia molecules. Other examples are given here like this. Here, the coordination entity is nickel 2 plus ion surrounded by 4 carbonyl groups. What about this? Here, platinum ion surrounded by 2 chloride ions and 2 ammonia molecules is collectively called as coordination entity. Likewise, this also. And come to the next term, that is central atom or central ion. So in the coordination entity, this coordination, the atom to which the fixed number of ions are bound in a definite geometrical arrangement is known as central atom or atom. Here, cobalt ion is the central ion in that coordination complex. Taking other examples, here in this complex, nickel 2 plus ion is the central ion. Here, cobalt 3 plus is the central ion, and in this case, Fe3 plus ferric ion is the central atom or central ion. These central ions are also referred as Lewis acid. So we have studied what are Lewis acids. What are they? Lewis acids are those which have a character of electron acceptance. So electron acceptors are known as Lewis acids. So metal ions are positively charged. So there is a valency of, so there is a tendency of this to attract electrons. Thereby they are acting as electron acceptors as well as Lewis acids. Now coming to the third term, that is ligands. Ligands are molecules or ions or groups that are directly bound to the central metal ion. Here in this case, the NH3 molecules, 6 NH3 molecules are known as the ligands. So there are 6 ligands, one central atom, and central atom plus ligand will constitute the coordination entity. So this ligands, so how can we write it as? Central atom plus ligand will give you what? Will give you coordination entity or coordination sphere. Both the terms are used, coordination sphere or coordination entity. What is the speciality? The coordination entity, the metal atom is surrounded by a number of ligands in which the spatial orientation is highly specific. And coming to these ligands can be of different types. They can be simple molecules, simple atoms or ions like chlorides. Simple atoms or ions like chlorides are chlorides or fluorides, Cl minus, F minus, Cn minus. These all are examples for simple ligands. Also neutral molecules, like we have seen ammonia, water molecule. These can also act as ligands. Ligands can have various chemical constitution. Also, larger molecules are also acting as ligands. For example, these molecules like NH2, CH2, CH2, NH2, or this one, and even macromolecules, very big size molecules like proteins can also act as ligands. So based on the type of bond that is, or type or number of bonds that is formed between metal and a single ligand, ligands can be categorized as unidentate, didentate, polydentate, etc. So we know what is uni. Uni means what? Unidentate means when the ligand is bound to a metal ion through a single donor atom. For example, this chloride, water molecule, ammonia. The ligand is connected or bound to the metal atom through only one atom. For chloride, it is bound with using the chloride ion. For water molecule, it is normally bound with the oxygen, the lone pairs of electron on the oxygen. Similarly, for ammonia also, it is bound via lone pairs on nitrogen. So such ligands are known as unidentate. Unidentate ligands. Examples are chloride, iron, fluoride ion, cyanide ion, water molecule, ammonia molecules, etc. And if the ligand can bind to two donor atoms, it will be called as didentate. So unidentate is there, didentate is there, and if the ligand can bound to the metal atom through many atoms, such kind of a ligand is known as polydentate. So number of atoms connected to the metal atom in a single ligand is the basis of this categorization. The example for didentate ligands are this: ethane diamine. Ethane diamine has the structure like this: CH2, CH, CH2, CH2, NH2, NH2. So it can go and form a bond with the metal atom via these two nitrogens. So these are known as didentate ligands. Oxalate is also the same. What is the structure of oxalate? Oxalate structure is like this: COO minus COO. This is the structure of oxalate. So in oxalate, the oxygen, these two oxygens can go and bond with the metal. This kind of an association can be possible. Therefore, it is called a didentate ligand. An example for polydentate ligand is given in the picture, that is EDTA, ethylene diamine tetraacetate ion. This ethylene connected to two amines, and in the amines, the NH2 H is replaced by acetate groups. So here, how many binding sites are there in this molecule, this ligand? So here, this is an example for polydentate ligand. EDTA 4 minus. It can go and bind with the metal atom through 6 atoms. It can go and bind using this nitrogen, this oxygen in this oxalate, then in this 4 oxalate groups. So it can, at a time, maximum it can go and go and form a bond with the metal atom through 6 atoms. So like this, for didentate and polydentate ligands, if more than two or more than atoms are used for forming bond with the metal. For example, like this. If in the case of oxalate ion, both the oxygens are used for making a bond with the metal, such kind of a ligand is called chelate ligand. This is chelate ligand. So what is chelation? Chelation means kind of a cyclic bond formation in the case of complexes. So to a single metal ion, 2 or more donor atoms are simultaneously bound, then it is known as a chelate ligand. The number of such ligating groups is called the density of the ligand. Density means how many atoms are used for making the bond with a single metal is known as density of the ligand. And from the structure itself is clear that these are tightly bound to the metal atom because two bonds are formed. So they are more stable, energetically more stable than the similar unidentate ligands, where only one metal atom, so one ligand is using only one ligand forming site for forming the complex. Now coming to the term called as ambidentate ligand. We have learned about unidentate ligands, bidentate ligand, polydentate ligand, and now there's a term called ambidentate ligand. What is this? Ligand which has two different donor atoms. at the time only one donor atom is used for forming the metal ligand bond. Such a ligand is known as ambidentate ligands. For example, nitro groups. Nitro thiocyanate ions are examples for this. The difference is that there are two electron rich sites in that ligand, but at a time only one atom is used for forming the bond with the metal atom. For example, in the case of nitrate ion, you can either coordinate through nitrogen or through oxygen. So at a time, only either nitrogen can form a bond with the metal, otherwise this bond will be broken and oxygen can form a bond with the metal atom. So at a time, only one will take part in the ligation. Similarly, thiocyanate ions can coordinate through sulfur and nitrogen. These two are regions of electron activity. But if sulfur is used for bonding to a metal, then nitrogen is not used. So nitrogen. So either sulfur or nitrogen can be useful in forming the ligand metal bond at a particular time. So now coming to the next term, that is we are going to study is coordination number. So that's a very important concept in coordination chemistry, coordination number or CN. So definition is like this: number of ligand donor atoms to which the metal is directly bonded. For example, here in our prototype, how many ligands are attached to the cobalt? 6. So here the coordination number of this cobalt ion will be 6. We'll take another example of platinum hexachloride ion complex. Here the coordination number of platinum is 6. 6 here. 6 chloride ions are attached. And for this example of this nickel complex, the coordination number is 4. Similarly, if we take this complex of here, the coordination number of ion atom is 6. Why is it 6? Because the oxalate ion is a bidentate ligand. It can go and attach using the 2 oxygens. So each oxalate ion will contribute to 2 bonds. So there are 3 oxalate ions. Therefore, 2 into 3, 6 is the coordination number of ion. So to metal, how many direct bonds are formed is the coordination number. So here if it is oxalate can form such a bond where a single oxalate ion will be bound to the metal through 2 atoms. So their coordination number will be 1, 2, 3, 4, 5, 6. And for this COEN thrice 3 plus. EN means ethylene diamine. Ethylene diamine means CH2, CH2, NH2, NH2. So each ethylene diamine molecule will be bound to the metal through two atoms using nitrogen. So each En will be contributing to a coordination number of 2. So like here 3 ethylene diamines are there. So here the cobalt also has a coordination number of 6. Because oxalate and ethylene diamine or ethane 1,2 diamine are didentate ligands. So this is how we are calculating the coordination number. Also remember that for calculating the coordination number, we will consider only the sigma bonds. If at all pi bonds are present, they are not taken into consideration by calculating the coordination number. Next, coming to the next term, that is coordination sphere. Coordination sphere is, like I said, it is similar to coordination entity, the central metal atom and the ligands attached to it, and those are enclosed in a square bracket. They are collectively known as coordination sphere. And what is this? What about this? The chloride ions here. So this is coordination sphere. And the ions that are outside the bracket, that is used for electrical neutrality, are known as counter ions. So a complex is made of coordination sphere and counter ions. For example, here the chloride ions are the counter ions, and this is the coordination sphere, CONH3 6 times. For example, for another example like K4 FeCN6, the coordination sphere is FeCN6 4 minus, and the counter ion is potassium ions K plus. And then we will go into the next term that is used called as coordination polyhedron. Coordination polyhedron, that is next term. That is the specific spatial arrangement in which the ligands are attached to the metal. So we have said there is no random, the molecules or ions are not randomly arranged around the metal ion. These can only occupy a special space, a spatial orientation in space around the metal atom. So spatial arrangement of the ligand atoms in which are directly attached to the central atom or ion is known as the coordination polyhedron. So we have told in the introduction part that the different geometries are possible for coordination compounds. So this geometry is determined by the coordination polyhedron, geometry of coordination polyhedron. May most commonly observed polyhedras are octahedral, square planar, and tetrahedral. For example, this cobalt hexamine complex polyhedron has a structure known as octahedral. Nickel tetracarbonyl is tetrahedral in structure, and this platinum tetrachlorocomplex is square planar in shape. So these three are the most common structures of coordination polyhedra. Other than the trigonal bipyramidal, square bipyramidal, all these structures are also observed in certain coordination complexes. M in this pictures, M represents the metal, L represent the ligands, unit-ended ligands. Now coming to the next term that is being used, that is oxidation number of central atom. Oxidation number of central atom is defined as the charge of that metal in a coordination sphere. If all the ligands are removed, taking the shared electron pair with them. So there is a metal and there is a ligand in the coordination complex. The number of ligands. So what is the kind of bond they form? They are electrons. Sharing of electron is happening. And if this ligand is removed together with these electrons, the remaining charge on the metal is called as the oxidation number. The oxidation number is represented by Roman numeral in parenthesis followed by the name of the coordination entity. For example, number of oxidation number of copper here is, what is the oxidation number? Cn minus. Cn has a charge of -1. So 4 minus 1 means -4 is the charge of this coordination sphere plus X, that is the charge on cobalt. Together they will give -3. That means X is equal to +1. So the how are you going to write the oxidation number of the copper? We will write Cu. Now open the parenthesis and write the Roman numeral 1. If this was 2, we'll write this as Cu2. And now coming to the next terminology that is commonly used, it's known as lepticity, homoleptic or heteroleptic complexes. In a complex, if the metal is bound only to ligands of the same type, these are known as homoleptic. Complexes in which metal is bound only one kind of a donor groups is known as homoleptic. For example, cobalt hexamine complex. Complex in which metal is bound to more than one kind of donor groups, these are known as heteroleptic. Lepticity is about the identity of the ligand. If single type of ligand is there, such complexes are known as homoleptic complexes. If more than one kind of ligand is attached to the metal atom, they are known as heteroleptic ligands. For this, we are coming to the end of this topic. Hope everybody understood it very clearly. If you have any doubts, you can ask me in the comment section.